Example 11.2, Goodness of fit test. In this example, we want to test the hypothesis or the claim from the employer that the day of absence out of a 5-day work week equally distributed over the 5 days. And we want to test it on a 5% significant level, so it's alpha equals 0.05. Now, the observation is that out of the 60 employees that we survey or in the sample, 15 of them absent on Monday, 12 on Tuesday, 9 on Wednesday, 9 on Thursday, and 15 on Friday. So we want to see if the absent days are equally distributed. What it means is, okay, out of the 60, if you equally distribute over the 5 days, so 60 divided by 5 equals 12. So if it's equally distributed, every day should have 12 absence. But right now, our observed data give us is seemingly not equally distributed data. But how statistically significant is this data? We have to use the goodness of fit test in order to see whether we can have an alternative hypothesis or alternative belief that absent dates are not or unequally distributed. So in order to test a goodness of fit of a distribution, we need the test statistic. And the test statistic, we call it chi-square. So it looks like an X, and then you put a square up for it. It's read as chi-square. So it's a chi-square statistic, and its formula is you use the observed value, subtract the expected value, and then you square this difference. You divide it by the expected value for each cell that you see up here. And then afterward, you add all the value up to get the statistic. So what do we mean by that? Well, you have an observed value 15, but you expect it to be 12 for equally distributed. And then you divide it by 12, okay? So that's how you calculate the first cell. For the second cell, you do similar things. For Tuesday, we observe 12 absent, and we expect 12 absent, and divided by 12. And for Wednesday, we observe 9 absent, we expect 12 absent, and we divide it by the expected value. Similarly, for Thursday, it's 9 subtract 12 square divided by 12, and for 5 days, 15 subtract 12 square divided by 12. Now you calculate all these numbers, but then at the end you have to add them up. So this summation is telling you to add up all these numbers. So you enter this expression into your calculator. You should be able to get the chi-square statistic is, okay, so I'm going to break down the calculation for you. 15 subtract 12 is 3. 3 square is 9. So 9 over 12 plus 0 over 12 plus 3 square is 9 over 12 plus negative 3 square, also 9 over 12. 15 subtract 12 is 3 square is 9 over 12. So use a calculator, or you do add those fractions up yourself. You get the test statistic chi-square equals 3. So what does it mean to have a chi-square equals 3, and how do we test it? Well, then we have to draw the chi-square distribution. And it looked like a normal distribution, except it's skew right. What it means is it have a long right tail. Okay, so what is the mean of this chi-square distribution? And we need to find a degree of freedom. And this degree of freedom is the mean of the chi-square distribution. Now, how do we find a degree of freedom? It's not n minus 1, okay? It's not a t distribution. The degree of freedom will equals the number of category or cells subtract 1. What do we mean by that? How many days do we have? We have 5 days, because Monday to Friday. So 5 category, we subtract 1, so the degree of freedom is 4. What it means is the mean of this distribution is 4. Now the test statistic we get is the number 3. What we want to know is this area. And this area is the p-value. It represents the probability of getting a test statistic equals 3 or greater than 3. So how do we find this p-value or that area? We need to go to our textbook. There's a chi-square table right underneath the normal table. You click the link, you'll be able to see this page. So you go down, you find the critical values for the chi-square distribution. Here we have degree of freedom equals 4. Okay, and you see the smallest number is 7.779, and you see on top of it is the probability is 0.9. So what it means? It means if you have the number 7.779 from the table, this area will be 0.1. And the area to the left of it will be 0.9. But now we have 3, okay? Obviously, this p-value, the area of the blue is greater than the area of the red, 0.1. And moreover, 0.1 is 10%. So it's greater than the alpha, which is 0.05 right here. So because the p-value is greater than alpha, we conclude. So our conclusion is that we fail to reject the null hypothesis. So you have to refer to the handout, right? We fail to reject the null hypothesis. So what if you want to be more precise of the p-value, right? So instead of using here is from the table, okay? From the table we can find out for this. But if you use a calculator, TI 8384, okay, we get the precise value for the p-value, okay? For chi-square of statistic of 3 and degree of freedom for 4, the p-value you can get is 0.5578. But as you can see, it is greater than 5%. Okay, so we fail to reject the null hypothesis. What it means is at a 5% level of significance from the sample data, so what we observe, there's not significant evidence to conclude that the absent days do not occur with equal frequency or equally distributed.